Hello. This lecture we will talk about the Morera's theorem. Basically, this theorem allows one to prove the holomorphicity and a weaker condition. So recall that before we have several characterization of holomorphic functions depending on the various regularity conditions. For example, when function f is smooth, then you can use the Cauchy-Riemann equation to test if f is a holomorphic function. When f is complex differentiable at each point, then you can use the second definition, and by the Cauchy-Coussin theorem, you can conclude that these two definitions are equivalent. And then here, we use a weaker condition, that is when f is smooth, when f is continuous. So the theorem is as follows. Suppose f is a continuous function in the open disks D such that for any rectangular boundary T contained in D the contour integral so let's see let's denote the boundary as gamma. So the gamma fz dz line integral is 0. Then f is holomorphic. So before we give the proof, we first make two remarks. The first remark, if f is holomorphic according to the definition 1 or definition 2, automatically we have the line integral is 0 by the Cauchy-Coussin theorem. And remark 2, so here first let's explain a little bit what is a rectangular boundary. At the beginning you have an open disk D, and then the condition is that for any rectangular inside the disk, and then you may have the boundary of the rectangle. So gamma just the loop, the red loop around the rectangle counterclockwise once. That's a usual definition for the boundary. Okay, and then remark 2 goes as follows. The contour integral vanishes for simple closed, for any simple closed polygonal path gamma contained in D with only horizontal and vertical sides. In other words, if you draw a picture, here I should use a loop. Path is okay because you already have closed. For any single closed, so you might draw a picture like the following. The red part go this way. As soon as each side is either horizontal or vertical, then the integration is 0. If f is, so actually, if f is holomorphic, then the above is true. Since D is simply connected. We proved that before. Okay, now let's prove Morera theorem. So fix a point Z0 in D for any Z in D. Draw a polygonal path CZ in D with only horizontal and vertical sides starting at Z0 and ending at Z. Now consider the function capital Fz defined by the integration of f c d c along Cz. Then f is well defined. In other words, it's independent of the choice of the path, polygonal path Cz, since the integration along any closed loop is 0 for a single closed polygonal path gamma contained in D with only horizontal and vertical sides. Why this is true? Because, so let's fix Z0, and for any point Z, if you want to define the value of capital Fz, then you need to draw a polygonal path. But different people might draw different paths. For example, someone would like to draw this path. So CZ prime, this is CZ. Okay, then you need to show this is well defined. How do you show that? Because, so let's see, this is an explanation. CZ minus CZ prime is a closed loop, then integration of efficacy decacy along this is 0. And if you separate two terms, you conclude the integration is the same as soon as you fix the ending point z. It's independent of the choice of the loop. Okay, now we would like to verify the holomorphicity by the Cauchy-Riemann operator. So we need to take a derivative. So moreover, if we horizontally adjoin a new side with starting point at z, and then apply the fundamental theorem of calculus. So if you draw a picture, what we are doing, you have z0, and now you just choose a path to define fz. And to define fz, now consider z plus h, where h is a real number. Then to define fz plus h, by definition, you can choose a path cz plus, let's call it iz plus z to z plus h. So where z plus h is the green horizontal line, horizontal interval. So z plus h. And the integrand is, of course, efficacy decacy. Okay, then if you compute the derivative of capital F with respect to x at point z, then what do you have? By definition, you need to compute the limit of the difference quotient. And if you use the formula star, then you conclude the numerator gives you integration along izz plus h efficacy decacy divided by h, and then by fundamental theorem of calculus, after parameterize the the curve, the line integral, you have, this is fz. Similarly, we can conclude that the y derivative of capital F at z is I times fz. Okay, then capital F z is holomorphic. Because it's complex differentiable at each point, and then by the definition, second definition, we know F is holomorphic. And then F has a power series expansion. In particular, F is infinitely differentiable. In other words, you can take as many derivatives as you want. Therefore, small f is infinitely differentiable. Because this is because small f is x derivative of capital F. Now we can use the first definition of holomorphic function to test the holomorphicity, because F is smooth enough to apply the Cauchy-Riemann operator. And since the second derivative is smooth, you can change the order. So this is you first apply the Cauchy-Riemann operator, then apply the x derivative. Okay, then you see it's automatically 0. Okay, see. Then we are done by the first definition. Okay, so next we will apply the Morera theorem to do some extension problem where the derivative is very hard to test the regularity. Even for the weak sense, the complex derivative in the second definition. The only thing we know is continuity of the function. So application 1, sequences of holomorphic functions. Actually, we mentioned this theorem before. This is if Fn is a sequence of holomorphic functions that converges uniformly to a function f in every compact subset of omega, then f is holomorphic in omega. Here omega is just an open set where f is defined. Okay, so the proof, since Fn uniformly converges to f when n goes to infinity, on each compact subset, and Fn is continuous. Then we can conclude f is continuous on omega. So the argument, if you are not so familiar, let me repeat. So let D be a compact subset of omega, then Fn uniformly convergent to F on D when n goes to infinity. Then by a theorem of the uniform continuity or uniform convergence in Math 521, we can conclude F is continuous on D. Since Fn is continuous. Okay, since D is arbitrary, F is continuous on the whole domain omega. This property actually is very commonly used in mathematics. That means if you have open set omega, you approximate or exhaust omega by a sequence of compact set, because analytic properties are better in compact set. If you recall what we learned before, when you discuss uniform continuity, differentiable, or whatever, you always work on a compact set, D1, D2, D3, blah, blah. So that means you have a sequence of compact set contained in omega, and the union is a whole domain. So this is called exhaust omega by compact subsets. That's a typical technique we will use in analysis. Okay, now let's turn back to the proof. Since F is smooth, F is continuous, then we can apply okay. Yep. Yeah, I should stay in this way. On the other hand, for any path gamma contained in a small disk, let's call it D. In omega, we have the integration f and z along gamma converges to fz dz integration along gamma when n goes to infinity. This is because Fn uniformly converges to F. To F. Okay, then we conclude this is true. For any rectangular boundary gamma contained in a small disk d in omega. Okay, then F is holomorphic in D by Morera's theorem. Since the holomorphicity is local, it's a local property, and you can choose a small disk D to be arbitrary in omega, then we can conclude F is holomorphic in omega. So think about this property. I should make a remark about the line integral along gamma. So I should first ask a question. Why should we choose D instead of working on the whole domain omega? This is very crucial. I give you an example. So suppose you have a puncture disk, and the function you have is 1 over z plus 1 over n. Okay, and converges to 1 over z. But now, if you choose your loop to be this one, let's call it gamma 1, then gamma 1 fn is different from 0. Okay, think about why. If you understand this property, then you have good understanding of the Morera theorem. Okay, remark 2. We can prove the above theorem by Ascoli-Arzela theorem as well. Then you need to use a little bit the mathematical analysis information, and here the crucial thing will be using Cauchy estimate to bound the difference of the derivatives when n and m goes to infinity. Okay. Probably you can think about how to prove in this way. Now let's give a second application, which is very interesting, geometric lemma. If omega is an open set in C, F is continuous on omega and holomorphic on omega, subtract the real number line, then F is holomorphic on omega. This is kind of extension of the holomorphicity. Okay, let me draw a picture. First, you have real number line, and then you have a domain omega. Okay, and the holomorphicity holds by the assumption only on the interior of the up half domain and the interior of the lower half domain. In particular, you don't know the holomorphicity for the points on the real number line. But now we want to test the holomorphicity on the real number line. You can think about here it's hard to apply the first definition and the second definition of holomorphic functions because you don't know the smoothness at all along the real number line. Moreira's theorem enables us to get rid of the complicated situation. So it suffices to check that line integral is 0, where gamma is the boundary of a rectangle. If gamma is contained in omega minus real number line by holomorphicity of f in omega in omega minus r, it holds, star holds. Then it suffices to consider the following case where the rectangle crosses the real number line. So this is real number line, and you have rectangle T. So let's denote the endpoints by B plus ID. Here A plus ID, A plus IC, B plus IC. Okay, then this is gamma. Since F is continuous, we can approximate the line integral as follows. You draw two horizontal lines starting from A plus IR to B plus IR and A minus IR, I epsilon to B minus I epsilon. But then the direction is as follows. The above one go from left to right. The line beneath go from right to left. Okay. Then basically you have two loops, which is very close to the original loop. You have some arrow, but since F is smooth, the arrow is 0 when you cut it finer and finer. So mathematically, so why this is true, I leave it to you. this is a limit when epsilon goes to 0 plus. The line integral a plus I epsilon to b plus I epsilon f c d c plus b plus I epsilon to b plus I d f c d c plus b plus I d to a plus I d f c d c plus a plus I d to a plus I epsilon f c d c and plus b a plus IC to b plus IC plus b plus IC b minus I epsilon plus b minus I epsilon a plus I a minus I epsilon plus a minus I epsilon a plus IC f c d c. Okay, now first 4 terms just the line integral along the loop. So let's call it gamma 1 epsilon. The one below is gamma 2 epsilon. So this is a integration along gamma 1 epsilon f c d c plus gamma 2 epsilon f c d c and take the limit. Okay, now the advantage of this cutting is these 2 loops are both in the omega minus the real number line. Then you can apply the Cauchy-Coushac theorem, which gives you 0. Okay, therefore the original integral along gamma is 0. F is holomorphic by Morera. Okay. By this lemma, we can establish a very interesting geometric property, which is called Schwarz reflection principle. Later on, we will apply it again when we construct conformal maps of some polygon to the upper half plane. And I should say, very interesting and vivid examples exist here, but I will not show at this moment. I will just prove the general statement. The question is like following. In general, it's very hard to extend a holomorphic function outside the original domain. It's easy to construct very weird domains such that the function cannot extend holomorphically outside. For example, how to extend the power series holomorphically outside the convergent region. later on when we study special functions, gamma functions, zeta functions, we will use another way to characterize this or give you some example, usually how we extend holomorphic functions starting from a power series. So here we give another geometric way as follows. Suppose you have domain cross the real number line. So this might be, let's use different color, gamma. This is your original domain, omega, and let's denote the up half by omega plus, lower half by omega omega hat, okay. And then what we want to do is reflect the up half to the lower one along the axes. Okay. We call this as omega minus. So we want to find holomorphic function defined originally on omega to be extended to omega union omega minus. It's not true that the extension exists when f is arbitrary holomorphic function, but if we put on actual condition, then this extension is possible. So the following is the Schwarz reflection principle. If f is holomorphic on omega, which is continuous on omega plus union omega intersection the real number line and assumes real values on omega intersection real number line. So this is an additional property we need to put on f. Then the function capital F defined as follows is holomorphic on omega plus union the part on the real number line union omega minus. Fz is defined by capital F defined by Fz when it's in the up half part, and the Fz bar the conjugate of Fz bar when z is in omega minus. So proof. So by Morera's theorem, it suffices to prove that f is holomorphic on the union and the union of omega plus and omega minus get rid of the real number line and continues on the whole domain. Okay, so first notice that for any point z0 in omega minus, fz has a expansion anz minus z0 bar to nth power in a small disk. Z minus z0 bar less than r, which is contained in omega plus, where r is positive. Because any point in omega bar has its conjugate in omega plus. Sorry, any point in omega minus has its conjugate in omega plus. Therefore, you can find this formula, and then for any point in z minus z0 less than r containing omega minus, capital Fz is conjugate of Fz bar, which is summation 0 from infinity an bar z minus z0 to nth power. Okay, in particular, capital F is holomorphic in omega minus. Therefore, the first condition holds. Next, since F is continuous on omega bar, omega plus union omega intersection R, and conjugate of Fz bar is Fz when z in the real number line. F is continuous on the up half domain union the real number line union the lower half plane. So I should say the continuity follows from the realness of F on real number line. So it's crucial. The continuity is not trivial. But anyhow, we prove the Schwarz reflection principle. In higher dimensions, if you're interested, there's very interesting Mosto Delin Picalettis, which is a generalization of the Schwarz reflection principle by the complex reflection. When you have more than one complex variables, it's very interesting. So if you are interested, I suggest you to choose this as your reading topics. It will involve the Picard-Fuson differential equation and monogamy groups, some topology, some algebraic geometry. It's very interesting. Next, we end up with another expansion, Laurent expansion of holomorphic functions on Annulus. So before, we already know how to do the power series expansion of holomorphic functions on disk. But for the later study, we want to establish a similar result for Annulus domain. Of course, you will see from the result, it's a little bit different from the previous case. So to determine Annulus, you need to give the interior radius and the exterior radius of my bed joint. Okay, so this is R1, this is R2. Let f be a holomorphic function defined on an open annulus R1 less than z minus a less than R2. Then Fz is summation of from negative infinity to positive infinity Cn z minus a to nth power on the open annulus R1 less than z minus a less than R2, where Cn is 1 over 2 pi I summation sigma minus a equals R f c minus a to n plus 1 d c. Here for n in z, so this formula Cn, the formula for Cn holds for any integers n and any real number between R1 and R2. Moreover, the convergence is absolute and uniform on any subannulus strictly contained in the original one. If you recall the previous formula for the coefficients appearing in the power series expansion of a holomorphic function on disk, you believe that here the coefficient Cn is independent of the choice of the real number R between R1 and R2 by Cauchy. Theorem. Okay, now let's give a proof. We take any point z inside the annulus, choose small r1, small r2 in between, such that z is in the small annulus, and then by Cauchy's theorem, Fz, Cauchy integral formula, equals 1 over 2 pi I summation 1 over 2 pi I integral along the exterior of f c minus z minus 1 over 2 pi I integral along the interior boundary f c minus z d c. If you draw a picture, this is R2, this is R1, and then you choose small r1, small r2, and your point Z is here. So if you do orientation, the outside one is counterclockwise, inside one is clockwise. Okay, let's denote first as R1, second integral as R2. By a similar argument, we want to expand the 1 over c minus z to a power series. So we do, this is the exact same as we did for the holomorph function on a disk. Summation m from infinity z minus a to n's power divided by c minus a to n plus 1's power for z minus a less than r2 equals c minus a. And for R2, here you need to be careful when we expand the denominator. We have different order. C minus a is less than z minus a. Therefore, when you expand, you have a negative power in z minus a. For c minus a equals r1 less than z minus a strictly. Therefore, fz, if you plug in, you'll find its summation from 0 to infinity z minus a to n's power. Coefficient is 1 over 2 pi I c minus a equals r2 f c minus a n plus 1's power d c plus summation 1 over z minus a to n plus 1's power 1 over 2 pi I times line integral along the interior circle. So this is the positive part. Positive part. This is the negative part. Next time we will discuss the singularity of meromorphic functions, and then we will talk more about the negative part. What's the difference for the negative part? What's the significance for the summand in the negative part? Okay, anyhow, we make a remark. The Laurent series expansion is unique. Okay, so how to prove it? Why? I leave it to you. It's also in your textbook. Okay, I will stop here.